Good evening, sir. Kamalesh, am I audible?
Yeah.
Yes, ma'am.
Yes.
Hello.
Okay, sir, let's wait for a few more minutes and then we'll start the session.
Okay. My mic is disabled, I think.
No, sir, we can hear you.
Okay, then it's fine. Okay, good.
Uh, so, sir, we are starting today's session with your permission.
Yes, sure.
Okay. Um, so, good evening, our respected speaker and dear participants. Welcome you all to the fourth day and seventh session of our FDP AICT Auto approved FDP on emergence of cloud computing, cloud technologies, and recent trends. Yesterday, I was telling you that outside of our college or some few persons are there who helped us to make this FDP reality today. Today's speaker is one of them. He has helped us a lot to make this program a successful one. I don't know how much successful it will be, but whatever it is, sir is one of them. He is none other than Professor Dr. Debashish De. So it is my honor to introduce our esteemed speaker, Sir Professor Dr. Debashish De. He will be delivering his first session of the fourth day on the FDP on emergence of cloud computing, cloud technologies, and recent trends. So before that, Sir actually doesn't need any introduction. Mostly all of us know sir very well, but still it's a formality. We have to do this. So I'll read out the formal introduction of sir. That is Dr. Debashish De is a professor in the Department of Computer Science and Engineering at the Maulana Abul Kalam Azad University of Technology, West Bengal, India. He received MTech from the University of Calcutta in 2002 and PhD from Jadavpur University in 2005. He is a senior member IEEE, fellow IET, and life member of CSI. He was awarded the prestigious Boycast Fellowship by the Department of Science and Technology, Government of India, to work at the Heriot-Watt University, Scotland, UK. He received the Endeavour Fellowship Award from 2008-9 by DEST Australia to work at the University of Western Australia. He received the Young Scientist Award in 2005 at New Delhi and in 2011 in Istanbul, Turkey, from the International Union of Radioscience, Belgium. In 2016, he received J.C. Bose Research Award from IIT New Delhi. In 2019, he received the Shiksha Ratna Award from the Government of West Bengal. He has published around 400 journals, 200 conference papers, 20 books, and granted 4 patents. His projects sponsored His projects are sponsored by AICT, UGC, WBDST, DST, World Bank, AWS, and Ministry of Electronics and Information Technology. He served as chairman of CSI and IIT Kolkata, a slate member of IEEE Communication Society. His H index is 46. The citation is 10,200. He is listed in the top 2% scientists of the world. His research interests are Edge AI, IoT, and quantum computing. So it's an honor for welcome you, sir. Sir, we are eager to listen from you. Over to you, sir. Thank you so much for joining the session again.
Yeah. Good evening. Thank you, Tapashi Madam, for your kind introduction. And I'd like to thank the participants. I think around 130, 188, 28 participants have joined. Maybe you are traveling, maybe you are in the evening time. So thank you for joining for in such a large number. And today I'll be just giving you some of the introduction of the work called mobile edge computing. So mobility is very important part of our life. We're all mobile in nature, so we like mobility, right? I think everyone like mobility. That is the reason the our landfall has exhausted, and all the devices around us is mobile, right? So we are not in wired domain. We are now totally uh, going towards the wireless devices, handheld devices. So today I'll be discussing on very basic topics on edge computing. Edge also is called edge cloud. So let's see how it works and how it behaves. Edge computing is now part and parcel of our life, and almost in every cases we use this edge computing in our day-to-day activities. Even our, if you see uh, the edge computing and IoT is actually synonym. You know that IoT is made for edge, edge is made for IoT. So they are work together, hand to hand. So if you want to study the IoT or Internet of Things, where you want to control anything and everything in this world, it should be edge enabled, right? So even your washing machine, desktop, you know that what is called that, even the chimney. Even you can control your chimney through your mobile phone or through Alexa, various wireless activities. They are all edge devices, right? So let me share the screen. Is the screen visible?
Yes, sir.
Okay, thank you. So today's topic I'll be discussing here is mobile edge computing for IoT, right? Edge computing for IoT. You know the cloud domain also we have discussed about a lot of edge systems. I think the mobile means mobility. You know, so for example, our drones are mobile, right? Your Ola and Uber, you can see they're all mobile in nature. So today I'll be discussing how this edge computing is helping actually this IoT, Internet of Things, right? So you know that computing has changed a lot. You know that earlier we used to have von Neumann architecture, right? Where CPU and memory, you know, any CPU, you know, in school level book you see CPU and memory work differently, right? And there is input and output. Nowadays we are in the age of neuromorphic computing, right? Even neuromorphic chips are available, neuromorphic laptops are available. If you want to purchase any recent version 2025 version of any kind of laptop, neuromorphic laptops are available, right? What is there? CPU and memory, they are working together. If you see our brain, human brain, what happens? In our brain, what happens is this brain, the memory and CPU is within. So it is called in-memory computing. Okay. So various terms are coming up called neuromorphic computing because we are mimicking the behavior of neurons like our human brain, and we are doing brain-like processing, that is called neuromorphic processing, where CPU and memory is working together. So memory is within the CPU, right? CPU and memory is working together. So in our school level, what you have learned, von Neumann architecture is no more valid, okay, in 2025, this year, right, onwards, right? Why? What is the reason? Because the neuromorphic is the future, right? We want faster processing, fast, ultra fast operation. So CPU to memory data communication is slow. So you need to resolve that. We are now putting CPU within the memory itself. So that is known as neuromorphic chip or neuromorphic computing, and that makes possible to develop this high speed ultra edge processing of this edge computing devices, right? So what you have seen that CPU and memory merged together for, earlier we have input output memory, see they're all together different, right? This is input output CPU and memory. This is known as von Neumann. In case of neuromorphic, input is there, output is there, but CPU and memory they are working together. So it is also known as in memory computing or neuromorphic computing, or sometimes called PIM, processing in memory, right? CIM, computing in memory, CIM, computing in memory, processing in memory. These are the terminologies that are coming up for last 1 year. Very recently this is happening, and this neuromorphic chips are coming up, which is at least at least 1,000 times faster, maybe 10,000 times sometimes faster compared to the conventional von Neumann architecture. So maybe in school level this architecture will be replaced very soon, because this CPU and memory is not different. They are working together, and the processing is happening. Because of this transmission cost from memory to CPU, CPU to memory, lot of energy loss is happening. To reduce this loss, we are using neuromorphic computing. Okay. So neuromorphic edge. So we'll be today discussing on the edge computing, that is called neuromorphic edge, where the memory can also process the data, right? That is a thing today I will discuss in detail. Okay, but this is a basic. What is the difference between von Neumann and neuromorphic, right? Now, in our university we have Center of Mobile Cloud Computing, Center of Mobile to Cloud, right? Mobile data to the cloud. So we do it regularly, right? We started this process a long time before mobile cloud computing. I have written one book from CRC 2015, 10 years before, right? So that book is on mobile cloud computing, means how this mobile phone data is basically operated using the apps, right? And the data can be accessed from the cloud using various apps, right? For example, you want Ola and Uber, you don't have to have any car, right? We can hire the car using this Ola and Uber app. You want to get any food using the app, you can go for Zomato or any other food, right? If you want to purchase any product, there are Flipkart, Amazon, Blinkit. You can predict. So this is basically this century is basically app-based network, right? Everything we rely on the apps, right? So, and that provides you the facility that we do not have to carry anything, right? Means only a mobile phone with internet connection, we can directly connect to the cloud, right? And the process of transferring the data from the mobile to the cloud is known as offloading, right? So if you see the current ages, that mobile cloud is so popular because, for example, you want to listen any video, any music. What you do, you can simply go to the YouTube and we can listen the music, and it is a matter of only few seconds, right? Earlier, my hobby was to store the music and store the videos for playing. So you have to collect the music. Now everything is available on your fingertip with this help of mobile cloud computing, right? Because data is going from mobile to the cloud. Now in our center, we do a lot of operations related to mobile to cloud. So that is the reason our center name is Mobile Center of Mobile Cloud Computing, where mobility is playing major role, right? Mobility. Right. And if you see that data mobility means that how these cars are moving, vehicular data. If you consider that which city is a smart city, right, where the vehicle speed is high compared to, say, suppose Bangalore versus Calcutta. So obviously, if you see that Bangalore is comparatively, in many cases, because of wide roads in Bangalore, Hyderabad is less congested sometimes. So we can call that from the vehicular speed, the average speed of vehicular data, Hyderabad is more smarter compared to Calcutta. Maybe Calcutta is smarter compared to Delhi because of condition, right? So these are the actually various measurements we do for vehicular data, data mobility, and crowd sensing. We can also sense the crowd. Sense means we can process the data, what the data is provided by the crowd. Each and every user can contribute and send the data to the cloud. Every user. So whatever you can take the picture, that picture is going to the cloud. So this process actually is known as crowd sensing. We are sensing the data from the crowd, right? If suppose there is an accident or there is some roadblock, automatically someone nearby will take the picture and post it in any social media, and the vehicle moving to that area, they can avoid that road because of condition, because of road blockage and everything. That is the beauty of mobile crowd sensing. So mobile crowd sensing is very, very popular. We also work in this area of mobile crowd sensing, right? We also work in the drone data. We develop the drones, with 4 wings, 6 wings drones, and we work in this drone domain, right? And drone is also edge device, one of the edge devices which operates. We do mobility analytics, geospatial analytics, smart city mobility management, traffic trace management, that how the traffic will move, which direction. We use also PSO and GSO to model the mobility model in the system. So these are the 6-7 areas we work in this area of mobile to cloud computing, right? If you're interested, you can see it. It's available online in CRC Press. Now your this devices like drones are also one of the edge devices, because they work at the edge and they have the sensors. They can take the picture, they can sense the what kind of data. That sometimes there is some weight of the drone. If the drone, if you give the thrust with the wings, if the thrust is higher, then what will happen? The drone will move on the sky, right? For example, the thrust lift is greater than the weight. Weight is the red line, and green lines are the lift. If the lift is more, then the drone will move on the sky. Drone is one kind of edge device, mobile edge device. Mobile means it can move, it works at the edge, so it is known as edge device. So computing at the edge is known as mobile edge computing, right? Hovering means when sometimes you have seen that drones are moving on the sky and waiting at a certain point. When then lift is equals to weight. Then you will hover in certain area, take the picture from that area. You have seen in many various occasions these drones are using this picture. Hovering is happening that way. Lift equals to the weight. Right? And if you have to go for a higher altitude, then you have to give more thrust, more green lines compared to this red line. So the drone will move on the sky. Now these drones, the wings moves in the two in the clockwise and other two in the anti-clockwise. Then only drone will move on the sky. If all of them moves in the same direction, simply drone will rotate. That will not go up. This is the working principle that that should be crossed, means opposite direction, right? Drone also can carry the weight, so it can move, and drones are nowadays available for various applications, right? Now this workshop is all about cloud computing, right? So everyone know already is maybe the third day. So what is cloud? Cloud provides services, right? What are the services? They provide the services called platform as a service, software as a service, and infrastructure as a service. PaaS, SaaS, yes. These are the three services we are getting from cloud data centers, right? I think yesterday also Shunirmal talked about this, how this cloud data works, and the cloud is we cannot see, but it provides the service. Now, what is the problem? What is the problem of cloud? If you want to send any data from your mobile to the cloud, it will move to your mobile to your college server or any local server, then it will go to the cloud. So it will take multiple steps, 1-2 steps, right? And if the server is in, say, suppose I am talking from Calcutta, if the server is in Mumbai, you say Amazon server is in Gujarat, Ahmedabad somewhere, data will move from Calcutta to that area and data will come back. So you understand, so much delay will be there in the processing. That is the reason we are providing a new service or new computing called edge computing, right? Edge computing. What is that? Your mobile phone is also now powerful. Earlier it has only maximum 1 GB RAM. Nowadays it has 16 GB RAM, 8 GB RAM is available with lot of capacity of storage. It can also compute a lot. So edge devices are now powerful. Edge devices are now powerful. It can perform a lot of operations together, right? And there is a billions of edge devices. Everyone's house, if you see your smart tap, smart washing machine, smart TV, smart watch, smart lights, everything smart. We are all in the smart world. We have smart rooms, right? So within the smart rooms, all the devices what we have, that can also compute in a very short, low level. That is called edge computing. That kind of computation on the edge called edge computing. These are the local devices. See, only few thousands of cloud, but billions of edge devices, right? So as you know, we are interested to work in the IoT domain. IoT means Internet of Things, where you have to control anything and everything through the internet. right? We can control the light of our house or fan of our house by using this uh, edge devices, right? So edge devices are very powerful, and at the same time it can operate in the local level. So edge device can do this support to the IoT devices very faster compared to the cloud. So if say a cloud takes several seconds, it can be done in nanosecond or millisecond. So at least performance will be increased 1,000 times, 100 to 1,000 times, maybe more, right? If you see the platform, that is the reason we are not always going to the cloud. We are performing all the operations in the edge. Just like that, if you have any problem, suppose you are in a college. If you have any problem in your class, what do? You talk to your class teacher, right? If the problem is very high, then you can go to your uh, a head of the department, right? We directly do not go to the principal or vice chancellor or directors, right? They are the highest top boss of the system. Similarly, the clouds are also top boss. It is lot of power of computing, power of processing. But the problem is delay will be very high. Data will go to the cloud with various steps and come back to the edge. So IoT is not possible using the cloud. Cloud with IoT is not possible. So that is the reason to enable the processing at the edge. We are talking about these edge devices. Right? If you have any Samsung or Apple Watch, where you can see that it can compute your heartbeat, monitoring, you can various parameters of your health. Right? And that is the reason edge computing is so popular. And as the most of the devices are mobile in nature, your smartwatch is mobile, your mobile phone itself is mobile. You know that most of the devices, that they can be mobile. So we are talking about mobile edge computing, right? But edge computing is very, very popular and efficient to provide the services at the IoT level, and that is the reason we are all talking about edge computing. So what are the advantage we are getting in edge? Anyone is there? Madam, are you there? Or any participant? Hello? Anyone is there?
Participants, please interact with sir.
Or anyone, madam also can know. Why we are going for edge? Why not cloud? I've just mentioned why we are now, or for a small problem we do not go to cloud, right? We do not go to principal or vice chancellor. Your class teacher is sufficient to handle, right? There are two advantages. What are the two advantages? It can be computed at the edge
Wait,
local level.
Sandy, it's
Yes, yes, yes. Carry on.
yes, Shorav sir.
Yes, you said it is handy, right? Why it
Yes.
is handy? Because
No,
it can
actually,
perform faster.
It's a sir in age the computations are very low because the resources are very limited.
Limited, yes, correct.
That's why the cloud computation is required for huge information if you want to process.
Cloud computing is required for large data. For
Yeah,
IoT, only small, low value, low storage. For that, edge is sufficient. Most of the cases, right? Suppose
data
your mobile phone.
processing faster.
Yes, faster. Because why faster? Because it's very close to you, right? Data devices are close to you. Faster means no delay,
Yes.
no latency. There are three advantages. No latency, number one. Number two, energy efficient. Data should not go long distance. Transmission cost, communication cost is high. But in case of local, there is no transmission cost.
Yes.
It is ultra fast. So it is fast, smart, Smart in the sense, the mobility and all the features. Fast means energy efficient, no latency. These are the advantages, 3 advantages. No latency means the delay will be less. So we are using this edge computing, right? Number one. Number two, it is no communication cost, so energy efficient and real time. Most important is the real time. If you want to drive a IoT enabled car, smart car, Tesla car, if your edge cannot compute, then it will go for an accident, right? And that is the reason edge computing is so popular. IoT and edge computing is almost synonym, right? IoT, Internet of Things, and edge computing is almost synonym. Why? Because without edge, IoT is not possible. Actually, edge is developed for IoT only, right? But sometimes if the data size is very, very high, only in few cases, maybe 5% case, we have to go for fog or cloud, right? 95%, 90 to 95% data can be processed at the edge, right? So we can save 95% of data, energy cost, delay. We can perform the operation very real time, right? And that is the reason we are talking about edge computing. If you understand this slide, nothing more. This is the main motto of our today's discussion, that everything should be operated at the edge, right? It can be your laptop, mobile phone, or your smartwatch. If you use Apple, if anyone has Apple smartwatch, it can do hundreds of operation very accurately. So Apple smartphones are very, very intelligent as well as smart and edge computing device, right? Because it can perform multiple jobs. Your health can be also monitored your the smartwatches, and precision is very high. So initially, that 2 years before, I told you that we have written a book called Mobile Cloud, right? So there is an old version. It should be mobile, not mobile cloud. It should be mobile edge computing, right? So edge should be there, right? So edge computing playing a major role in our day-to-day activities. Now something is there called fog. What is fog? Fog is a, say suppose you are in a college, your college has some server or local servers, local authority, that is called fog. If the data size is very high, it can be done in the college level. So that is called fog. Okay. So edge computing is within yourself, within the user. Fog computing is within your company or your local vendors or at your college, your servers and GPU, CPUs. And the third is the cloud data centers. So these are the cloud data centers. So these are the 3-layer architecture: edge computing, fog computing, and the cloud. Obviously, cloud is so powerful, but cloud takes a lot of time, lot of delay. For small data, if we can conclude, for small data, we can process at what? At the edge. For a little bit bigger data, we will go for take the help of the fog. If the data size is very, very high, you are taking data for 1 year, then you have to go for cloud. But you are taking data for 7 days, maybe the edge is sufficient. If you are taking the data for 6 months, maybe you have to go for fog. If you want to take the data in years, 2 years, 3 years data, then you have to go for cloud based network, right? So this is the actually basic working principle of cloud, fog, and edge network, right? So 90% people now working on this edge computing at the edge, and many of them are neuromorphic. So on in memory computing. So in the memory you can compute, right? Processing in memory called PIM. Processing in memory called PIM or SIM. Computing in memory. So processing and computing, everything can be done on the memory within the chip itself. So these are called neuromorphic chip, right? So last week I was there in Bangalore. We have seen the neuromorphic chip. If you don't know, you can search. If you're interested, you can search on neuromorphic chip. The big companies like Nvidia, Intel, AMD, everyone came up. This NFX, there are various company. NXP Semiconductor, they also developed neuromorphic chip. Ultra fast and reliable lightweight chips are already developed, right? So edge computing is not a mystery, it's already the reality, right? We are all using this edge computing day to day. Now if you see the smart cities, suppose there is a drone, the drone is also edge device, right? You see multiple drones, they work together called Internet of Drones, right? So they are also edge devices, they can compute, they can perform the operations, they can work together, and they can provide the services within the city. For example, this drone can work for traffic light control, right? If there any road accident or any traffic signal violation, drone will move, take the picture, and send the data. If the traffic light violation, then the car will get a ticket. Means the punishment, means the ticket you will get, right? So these are the smart homes where you can see the drones are actually performing these operations at the drones and giving the health services for the senior citizens. Drone is acting as a doctor, is basically service doctor to provide the services at the room. If you have to connect it with any hospital, the drone will move and provide all kind of edge device services, right? Similarly for smart grid and smart applications. So most of the data is not going to the cloud. Most of them they are working together in the edge only, right? We are not going to the cloud level. Now how if it is a drone or any kind of mobile device, they are learning in the air, right? Because they are flying in the air. So learning, machine learning is happening in the air. What they are learning? Can anyone tell what they are learning? You can also type, no problem. The type option you can type also.
Participants,
They're
you can raise
learning.
your hands. Yes, yes, sir. I'm just give me a minute. Yes, Umar Farooq, sir, please.
Learning the environment, sir.
Yes, environment they're learning. What kind of environment? They're learning how to fly with the intelligent flying, right? They know that how to not to collide. There are multiple devices, right? They can collide to each other, right? Collision. Say suppose hundreds of drones, they should not collide. Have you seen the birds are flying and in the sky? Hundreds and thousands of birds are flying. Yes, have you seen it?
Yes, sir.
Do they collide and fall down on the ground?
No, there will be a consensus, something like some leader. That is one way.
Radar. How the birds or radar is coming?
Leader. When they are flying as a triangle shape.
Okay, triangle shape. Yes, leader. Yeah. So they do not collide, right?
They collaborate.
They collaborate. They do not collide. So our target is that how to collaborate. Yes, you are correct. How to collaborate with multiple drones together. How to collaborate with multiple edge devices. They are all edge devices. They can sense. Suppose this drone is going for sensing certain data in the war field or agriculture field or in various smart city applications, right? They're collecting the data. They're collecting how to dividing. Okay, asking to okay zone A is doing zone B. They're dividing their job, distributed fashion, right? As you said, collaboration, not collision. So how they are collecting the data in the edge level, that is actually the our motto, learning in the air, right? Edge learning in the air. Yeah. So the term comes mobile edge intelligence. We're talking about, so far we are talking about mobile edge computing. Now I am talking about mobile edge intelligence. We have to provide the intelligence, right? As you know, the machine learning is so popular. So when the drones are flying, their machine learning is there. that shows the confluence between the mobile edge computing and AI. How this AI and edge is working together, right? We're calling it mobile edge computing and AI. They are working hand to hand together to perform certain operation in the system, so that system can work efficiently, right? Yeah. So this is the actually motto of our mobile edge computing, in a collaborative fashion, how we can provide the intelligence. So various lightweight machine intelligence techniques are coming up to provide the services at the edge level and provide these high-end operations, means computing operations and everything. Right. So there is a definition of mobile edge, that multi-access edge computing, or known as mobile edge computing. The definition is that enables cloud computing capabilities and its services, IT service environment at the edge. See what is written? It enables the cloud computing capabilities. That means what are the service cloud can provide? That is a lower version of cloud, right? It provides the IT services at the edge of the cellular network. You know, some governments started their services at the doorstep, right? In West Bengal also there is a something scheme called Duwade something, you know, Duwade Intel. You know, they are providing service at the doorstep. The citizen do not have to go to the government. Government is coming to you. They are providing cloud. You do not have to go to the cloud. Cloud is coming to you. Provide the services at the edge, isn't it? So these are the services we are getting, uh, called mobile edge computing. What we are getting? Cloud computing enabled capabilities and IT service environments at the edge in the cellular network. Okay. So we have written 2 books. 2 years before I have written these 2 books. First one is called Mobile Edge Computing. I think if you're interested, you can go to Springer link. You can get this version of this. Almost 22 chapter it has, and we have discussed how to develop this algorithms and how to develop various kinds of offloading techniques. You know, how to data is going to the edge and how the processing is happening. So those who are interested, they can go through the details of this book. How this mobility and intelligence, they are working together. A second book we have written called on artificial intelligence for Internet of Things, right? How to provide intelligent IoT or AIoT, right? Intelligence for Internet of Things. So these are the 2 book covers more or less the basics of how the intelligence means, how this edge works and how this IoT based intelligence works. Now our target is to make intelligent mobile edge computing, right? That means you have to make the machine learning algorithms within your edge devices, within your drone itself, right? You can burn a drone. Burn means using a Raspberry Pi. You connect a IoT device, it can become an edge drone device, right? So we are providing this intelligence to the drones, to the networks itself, right? This intelligence has 3 levels. Cloud level. I think Shunibal, I think may have discussed about this centralized intelligence yesterday. How machine learning works in cloud level. Now I'm more interested in edge level. So we are talking about terminal intelligence. Cloud intelligence is called centralized intelligence. Now I am talking about terminal intelligence. What is terminal? Your car must know where to move the wheels, right, or the direction. Your drone must know where to fly, what to capture, how to fly autonomously. So this is called terminal intelligence. What to do and not to do, this kind of things can be prepared from the terminal intelligence, right, from this computation, caching and data. So in edge computing, we are more interested in terminal intelligence, right? Can anyone tell me that whether this centralized intelligence and terminal intelligence is same, or what is the difference? What is the basic difference between the centralized intelligence and terminal intelligence? What is the difference between centralized intelligence and terminal intelligence? Terminal
Segments
intelligence
are
is meant for
resource
yes,
constraints.
yes, resource constraint. So in case of cloud, you can have deep learning technique, right? Or explainable AI or various high-end techniques you can use, right? But in case of edge computing, you have to provide edge intelligence or terminal intelligence, because that means the deep learning will not work. Which algorithm will work for central intelligence or local intelligence, that is not possible for terminal, because resource constraint. Only 6 GB RAM you have or 16 GB you have. You do not have 1000 GB, but cloud has 1000 GB RAM, right? So you have to go for lightweight version of your algorithm. Lightweight means lightweight version of deep learning or lightweight version of say explainable AI or whatever, or transfer learning or reinforcement learning. Lightweight version, computationally lightweight, because here the processing is happening within the memory itself, within the chip itself, and the processing capability is less. So this place has lot of research areas, and believe it or not, this is the area almost the whole world is working. Terminal intelligence, right? In a Bengali term we call it funnily that Duware intelligence kind of thing. Like Duware Shokar, we are providing the service at the doorstep. We are providing intelligence at the doorstep, right? And it is done within the itself. See, very simple that your suppose you have a smartphone. Smartphone must have that lightweight algorithm within itself, so that the chip can understand what is your BP, what is your heartbeat, what are your health parameters, right? What is your pulse? It can understand. It is possible through the lightweight version of these techniques, right? So this area is very interesting research area for lightweight algorithms and lightweight machine intelligence, right? Yeah. Now, after say intelligence, suppose you have seen a bird, right? Do you need any bird? Need any instruction to fly? No. If bird sees something interesting, bird will fly, right? This is a very famous song of Shilajit. So it shows that bird will fly automatically. No need to control. You have seen the drones. Someone is controlling the drone. Nowadays, some drones are available, which is autonomous. They can fly like a bird. We call it autonomous drone, right? An autonomous drone, suppose in the traffic signal, if they found two people lying on the floor, drone will capture the image and send the signal to the hospital, and the ambulance will come. So drone is doing autonomously. So it's doing edge computing at the edge, right? But if there is any fire, drone will send the instruction in the control room. They will send ambulance as well as a fire brigade, right? So drones can perform these operations automatically. And see, the edge computing has lots of applications, infrastructure to agriculture, mining, every industry. Edge computing is so popular. Everyone is using the edge computing. Agriculture, one of the largest area in India. So when multiple drones are working together autonomously in a collaborative fashion, they are providing the pesticides and everything in a very fast operations. So these drones can handle huge amount of data: volume, velocity, and variety. These three V's are very important for big data analytics, right? Now this edge computing devices with lightweight SSD drives, it can carry 2 TB, 5 TB data on the drone itself. So it can handle huge amount of data, right? Volume, velocity, and variety. So if you see the IoT and the drone working together, it's like elephant, almost, right? Because elephant means, it is huge data it is carrying, right? Like an elephant, not elephant. It's similar to like an elephant, that elephant is flying, right? So when drones are so powerful, it's like Vandrik, right? It is flying on the sky, and it is doing the operations at the various levels in the border area, and also the this Drones are also working in the that various agricultural fields, also in the mining areas. Every place the drones has a lot of applications, right? Now, when you're talking about edge computing, we are not only talking about the sky. Drones are also, that AUV UV network. AUV means aquatic. So our target is to connect the on the land, on the sky, also under the water. So we need aquatic vehicles also. Aquatic means under the water, right? In my hand, this drone is actually aerial drones. I will show you after some time that we'll be using aquatic underwater drones. Aquatic. So within the water, drones can work and they can make a network. So our target in edge to connect three layers, right? What do you call Shargo, Morto and Patal? Means three layers, three lok we have to connect, right? Three lok we have to connect. Now, if you see the edge computing capabilities, it can fly, it can crawl, it can talk. These are the properties, right? It can recognize the face, it can climb. Even the delivery will start with the edge devices. Even in some places, Newtown or some places, or somewhere in the various other countries, the delivery is done through Flipkart, Amazon, through this delivery system, grabbing the object and sending the data. And they can give each other space. They should not collide to each other. I told you multiple times that drones are flying, they are flying like a bird, they should not collide. So these are the properties of edge, right? Any kinds of edge devices, autonomous edge device, right? That means no need any instruction. It can do it operation autonomous. So these are some of the edge devices, drone devices in our lab. This is the hexacopter, that not 4, 3 plus 3, total 6. So these are the properties of drones that it can sense, it can process the data very intelligent fashion. We call it intelligent drone. It supports edge, fog, dew, various level of data balancing. Now these are the areas actually drones are actually working together to perform the operations in a very high QoS quality of service it can provide, right? This is the basic structure of the drones and our edge devices. These are the electronics part. I'm not going in the circuits, but we develop the circuits for various levels. First level is the sensing layer or perception layer, right? Second level is the edge layer. Sensing means sensors, right? Then edge layer means the drone or mobile phones. They are all edge layers, right? It can ability to process at the edge. Then the gateway layer or the fog layer. Then on the top there is a cloud. We will not go to the cloud all the times. We'll go when it is ultimately necessary and huge amount of data, right? But generally we will process from sensor to the edge. So these are the multi-tier architectures of the edge. These are some of the research areas: routing area, mobility model, network integration, privacy and security is a very, very interesting area. And another area is called intelligent data processing. You have to process the network data very efficiently with the help of the machine learning techniques, reinforcement learning technique, federated learning techniques. So we can process the data very efficiently like this. We have published one work called Edge Drone, where we have maintained the quality of service for using a protocol called MQTT, Message Queuing Telemetry Transport Protocol. This is MQTT is very popular protocol for IoT applications. Most popular protocol of IoT is MQTT. So we developed various edge computing device for intended drones applications using this MQTT. Our target is to provide high quality of service, right? So this is the ecosystem where drones, multiple layers, how the protocols works, right? Skipping this. Now, for any kinds of edge devices or the mobile edge cloud devices, we need the quality of service. QoS. QoS means quality of service. QoS 0, QoS 1, QoS 2. QoS 2 is the highest quality. So if you go to any hotel, we have deluxe room, super deluxe room, VIP room. QS is VIP, like VIP, because high quality. How it happens? Suppose in QS0 there is a pub sub model. Pub sub means publisher is one drone or any edge device, subscriber is also edge device. Suppose two drone or two edge device, they want to talk to each other, they are taking the help of a broker called MQTT broker, right? Broker knows which drone is available, which subscriber is available. Accordingly, the broker will send the data to the related or rather available subscriber. So we call it pub sub model. MQTT works in the pub sub model in IoT devices, right? This is QS0. Here you can see connect, establishment and path. These are basically return paths. See here 2 lines and 3 lines, right? If you go for QS0, here it is 3 lines, 4 lines. So we are giving acknowledgement also. Reliability is high. So we are going for one level up, QS0 to QS1. But same pub sub model, publisher subscriber model through the broker. Similarly, if you go for QS2, see various other acknowledgements are coming up to provide very high reliable services from one drone to other drone, one publisher to other subscriber, right? Suppose we are now in this FDP, so I'm the publisher here. Because since I'm talking here, so through the this virtual platform, there is a broker. I'm connecting that 100, 200 people. So they are all the subscriber. You are listening something to me, right? So multiple subscriber is possible. One publisher and multiple subscriber. And Google Meet or Zoom, or these are the brokers, or Team Views. They're all the brokers, right? Here, through which actually, if you're getting very good reliable service, you have to pay more. See, more connections, more acknowledgements means more you have to say in a VIP room with air conditions, with fridge and so many services, right? You have to pay more. So QS2 is more better service, but this is the service areas, right? So what I have shown already in this picture, that one publisher can serve 3 subscriber, 1, 2, 3. Suppose there you are 150 participants. So 150 participants, they are all the sub nodes 1, 2, 3, 4 up to n. N means 150. One drone can operate 100,000. This is the beauty of scalability of IoT, and that is possible in this environment of edge, right? Scalability means it can operate for 3, 30, 300, 3000, any number it can operate using this MQTT. Right? So this way actually we can establish the connection from one master drone to the other drones, right? So these are some of the parameters we see in the bandwidth, timing calculations and other ones. Okay. I'm not going in details, but one thing I can show you that our target is to develop the drones which is less energy efficient, means more energy efficient and less power consumption. So some of the new techniques are coming up called energy harvesting techniques, so that drones can fly not only for half an hour, it can fly at least 12 hours or something like that, using energy harvesting technique. It can generate, the movement of the drone can be converting to electrical energy. That is possible to develop, right? So these are some snaps of our field work. This is executor drone. This is our drone deployment on the ground. These are the ground stations, and this is the autonomous drones, right? Now this is the drone works in the under the water. You can purchase it from Amazon or something. The underwater drones, and these are the 2 searchlights. This is the camera. 2 searchlights. This is the camera. This camera can take the picture under the water. Why? Our drone target is to connect this drone with the underwater drone to on the sky drone or on the land drones, right? So the underwater drones play a very important role for gathering or capturing the data from the under the water, right? But there are a lot of research issues are there because of density of water and pollution in the water, and visibility is another very important issue. What is not available in case of normal drone, visibility is not a problem, but visibility is a big problem for these edge drones, right? So you have to model the drones, you have to develop the software defined model for IoT applications. Anti-drone is also nowadays available, right? So that we can this edge, not only drone, any kinds of edge device can be also blocked, using this anti-drone. It's like a jammer. I think you have seen this picture in the during the various wars like Israel war and Russia war. Drones actually can attack the one country to other country. This anti-drone is actually to block the attacks for any kinds of edge devices, not only drone, other any kinds of edge device. It can sense, it can block the drones, right? Now, provide the security of the drones. Sometimes we use blockchain technology in the IoT domain, in the edge level. We call it drone chain. One drone connecting with other drones, using this blockchain. Blockchain means one can give the hash to other. If the hash matches, then it will transfer the data. If the hash does not match, it will block the other drones, right? So that is a operation of blockchain. So we have written one book, I think 2-3 years before, with Joel and Siddhartha, with blockchain based IoT, and where we have given that how drone chain works, how this drone chain is working together, why we are giving so much security to these edge devices or drones. Because if someone hack your drone at the border area, your drone will be used against you here. So we have to make them secure. So third party cannot control it. So we have to provide hash from one drone to other drones. But a lot of research issues are there. That computing issues are there. So a lot of people are working in this model of how the drone can operate and share the data from one block to other block, right? So anyone is interested, they can go through this book, blockchain based IoT, where you'll see there's one chapter called drone chain, where how this edge computing can be used for various applications for blockchain based systems to provide the services at the border areas and various secure zones, right? Where we cannot allow any intruder to attack the system, right? So blockchain based IoT is so coming very popular for security purpose and privacy purpose, right? There's something is called glow bomb. Have you seen this glow bomb? We call it Bengali Jonaki poker, right? So it's basically one kind of nature inspired computing, right? We have developed one book also called Nature Inspired Wireless Sensor Network, where you can see the Jonaki or the glow bomb. They are under the cave or anywhere in the jungle or in the remote areas. They fly by themselves, but they never collide. So we use this similar working principle of PSO and GSO, and we did some modeling on these drones, and using this behavior, we have deployed the 100 drones together in this model, and we developed the model for flying ad hoc network using this GSO, global sum optimization. This is by Ali Khan in 2019. After that also we developed certain model for flying ad hoc networks. Okay. This is our model. This is my paper 2020, 5 years before, where we have considered the movement based mobility. Basically they are mobility based model. Why? Reason is not to collide, providing this intelligence using global sum optimization. We published in ad hoc network LCWF 5 years before. Also we worked on fuzzy model. Fuzzy based systems can be used for path movement, means how the drones will move, path movement, right? The path optimization. So we use various fuzzy models for path movement in wireless sensor networks or drone networks. I'm not going in details, and even you will see that this edge device like drones can be used for lighting. Drone lighting system is very popular nowadays. If you see any IPL match or Olympic match, you'll see your light, your college name, or if you write India on the dark sky, this drone will fly on the sky and they'll make this pattern. How it is possible? Earlier, these are the matrix, drone matrix. They're all on the same ground. You have to program it from the controller. This drone will given a coordinate, and according to the coordinate, it will fly on the sky and make a position in the like a guitar or like a map of India or like any other birds kind of thing, right? Anything can be mapped. Just by providing the coordinate, drone will move to the sky without any collision and they'll make the patterns. So 3D lighting patterns, pollution free patterns. See, that is the reason I've given in that pollution free Diwali or pollution free lighting systems. That's so popular. It is only possible for providing this intelligence at the drone level or edge level. So that is the beauty of mobile edge computing, intelligent mobile edge computing, providing this pollution based, pollution free lighting systems. Maybe in Delhi or various areas where they can celebrate this drone lighting based systems, right? Drones are also used for social network. I'm not going in details. Also, we worked for healthcare using stride analysis. So there's a lot of edge computing devices are actually happening. You know, stride analysis. You know that within the foot, you know, if you have any, we have one project called foot analysis. Foot analysis means you are wearing a wrong shoe. If you use this edge based shoe, means you are putting a sensor. If your shoe texture is defective, you will get an alert on your mobile phone that is the time to change your shoes, right? If you are wearing a wrong shoe, your that neurological disease will start, right? So edge enabled shoes are also possible. Very simple sensors you can put and you can gather the data and measure the shape of the shoes and providing this intelligence. So we publish this work using stride analysis. Stride means how the person can walk. So we develop this model and providing these smart shoes operations, right? Now the question is when you're talking about the drones, right, or any edge computing device, what you have discussed that it must have internet connection, right? Can the drones can operate without internet? Answer is yes. If the internet connection is unstable for say 30 seconds to 1 minute or maybe maximum 2-3 minutes, then dew computing is the solution. We published one paper in IEEE Consumer Electronics magazine that how this dew computing is helping these drones to operate faster fashion, very fast drone can operate. We call it dew drone. So without the help, there is a cache memory in your system, cache memory on the chip. We call it caching. This is the dew computing is possible. Using this cache memory, if the data is lost for a certain amount of time, we can recover it using this cache. Data will be stored in the cache for 30 seconds to maximum 2 minutes, 3 minute time. If the drone lost its position and you will come back within 2 minutes, there will be no data loss. So that is called dew computing, right? So this is also cache-based computing, and this edge computing is used for various applications in disaster management, right? We published this work called Disaster Aware Internet of Drones. We published in IEEE transaction on consumer electronics, where edge computing we are getting the data from the edges. Suppose there is any disaster where main infrastructure is gone. So edge computing, edge devices are then used to provide the data so that we can understand where is the life, right? During the disaster, someone within the debris, right? You can find out using the sensing technologies, edge computing. You can find out where is the life. Now, these are the techniques we can follow. Also, drone is used for blood bank. Find out the exact blood group, AB positive, O negative, whatever. This is also used for edge computing for faster delivery of blood group from the nearby blood bank. This is also done by Internet of Drone Things. This is one of the application of edge computing. Suppose edge computing knows some person is there who want to use his blood and his blood group is say AB positive. It will collect the data from the nearby zone and deliver to the person based on the request of the doctor or the nurse, right? So these are the various ways of edge computing to handle the blood bank delivery and all these things. Okay. So last part of my discussion today is called federated learning for drones. What is there? In federated learning provides scalability, privacy and performance. These are the three areas. Scalability, performance will be high and privacy will be high. Scalability means 100,000, 10,000 people you can accommodate. Still machine learning will work. So this is also known as distributed machine learning, right? This is one of the techniques used popularly for various applications, right? What is that? You can see in this picture, there is a mobile phone, there is a tablet kind of thing, and there is a car. These are all mobile device, agreed? And after the data, after the learning, the mobile is learning at the local level, the data will go to the mobile phone to the cloud through this axis W1. Similarly for other, it is going to W2, WK, K number of devices. After getting the data is processed at the cloud level, and this processed at the cloud very faster fashion. And this is known as aggregation, called global aggregation. And after aggregation, a new model is generated. Can you see these blue lines? W is a new model which is generated after sorting at the global level, and the data is going to the cloud level. So by this way, actually, we are getting a cloud model or machine learning based model for the every user, right? So what actually happens? We have actually 1000. Is it clear or not clear? Anyone? Anyone in this click? Is it clear how this?
Participants, if you are having any query, please ask. Sir is there.
Yeah. Still, we have 15-20 minutes time. We can
Yes, yes, sir.
This is not a so easy phenomena. So basically, they are local learning and local level, edge level, and aggregation is happening in the fog layer or somewhere by the master drone. Right.
Sir, can you explain any one of the algorithm?
This is the algorithm. See, this is the algorithm for local learning, local machine learning, right? And W1 is going from the drone towards the global drone. This is the global drone, right? Can you see this W1? What is the direction of the arrow? From the mobile to the central drone, right? Hello? Similarly, this is W2. W2 is from the device to the central. It can be fog or it can be in a central server. So by this way, can anyone see what is the direction? What is the direction of W1? W1 is a user 1, user 2, user 3. So drone 1, drone 2, drone 3, or mobile, cloud, whatever, edge devices. They are all edge devices. Your car is also edge device, mind it. Autonomous car, they are also edge device. Mobile phone or tablet is also edge device. Whatever we are performing, any kinds of machine learning is happening at the edge is going to the upward direction. W1, W2, W3. Madam, is it clear? Understand? So whatever we are sensing, data is processed at the central zone. This is called distributed learning because we are learning from various distributed areas. Right. So see here also we have multiple drones. W1 is going to a central, W2, W4, W5. After that there is a summation or aggregation. Then the global model WG is generated, and WG is the global model. The WG is going to everyone's mobile phone. So this is also known as federated learning or distributed learning. Okay. Can you hear me? Yes.
Yes, sir, you are audible.
Yeah. So by this way, actually, global learning from the edge devices will go to the local level. So there is a global means there is a master drone can process the data and send the data to the local drones, means edge drones. Right. So this is the distributed mobile edge computing, distributed mobile edge computing, and machine learning is happening. Learning is happening at the local level, called local learning. Here RL means reinforcement learning, right? Local reinforcement learning to global reinforcement learning. They are doing summation. So we are getting the data from each and every user. After that, we are generating a global data, WG. We are getting data W1, W2, W3. We are generating a global data called WG. And that WG is distributed to all the drone itself, right? By this way, actually, we are performing this whole operation. And by this process, when WG is generated, there is no disclosure who is contributed. Everyone is contributed, right? So everyone's identity is not disclosed. So it is also known as privacy preserving learning technique, distributed learning technique, right? Where the privacy is not disclosed, right? Identity of U1, U2, U3, U4, UN is not disclosed. But at the same time, we are generating a global model, taking the contribution from each and every user. Edge drones, right? So this is known as distributed learning. If you write in the algorithm format, it will become distributed learning format. Very simple. First, algorithm means input. What is algorithm? Algorithm means a first input. Input will be the users, and there is a master drone and slave drones. Master slave, no, I told you the brokers. So one data will come here, W1 local learning, W2. After that, when all the data come to the global level, there is an aggregation, summation. After the aggregation, the global model is generated, called WG. Okay. This WG is the powerful model. It is similar to our WhatsApp, right? Everyone use WhatsApp, more or less. Yes or no? No one uses WhatsApp. Hello? Madam, are you there?
Yes, sir.
So in WhatsApp, what happens? The WhatsApp server, they are taking the data from every user from the edge level, right? On your mobile phone itself, everyone's mobile phone on your keyboard, it is happening. You are getting some recommendation, right? Through NLP. So local learning is happening on your mobile phone itself. All the local learning is happening on your mobile phone itself. That is called W1, right? Suppose it is happening in Taposhi Madam's mobile phone, W1. It is happening with Oren's mobile phone, W2. It is happening in Nilanjan's mobile phone, W3, up to WN. We are getting the data from all the users and it is aggregated. And after that, you are getting the new version, WG. And that is the data will go to everyone. But similar thing happened for our WhatsApp, right? Everyone's mobile phone is contributing. The data is going to the WhatsApp server. What you type, what you like, what you eat, every time we type, right? From that, it is extracting the data from the intelligence of the server or the or the master, that they do the searching. After that, after NLP, they send the data to all the users. It is similar to our app update. We update the app, right? Sometimes update of app is very common. When you update, there is any update of app, WhatsApp, anytime update comes. Every app there is update, right? And that is called the global model, WG. Because from the local learning from your keyboard, this system is learning how it happens, right? This is actually operation of this system, right? So
Shefali Verma, madam, I think you have raised your hand. Do you have any query to ask, sir?
yeah, okay.
Shefali Verma, madam, you can unmute yourself and you can ask your query.
Yes, madam.
Sir, am I audible?
Yes, yes, you are.
Yeah, good evening, sir. Sir, I wanted to ask, is there a difference between mobile edge computing and fog computing?
Totally different, because edge computing, I told you, I'm showing you the edge computing is your mobile phone itself. Edge computing, okay. Fog computing is your server of your college. Yeah.
Okay, sir.
Say, suppose I'm just showing you again this slide. Can you see this slide?
Yes, sir.
See, this is mobile phone, laptops, your smartwatch. They are all edge devices, right? If the edge device can move, it's called mobile edge device, right? Like a drone can move. I have shown you mobile example of drone. That is edge device. At the same time, it can also move. Yeah. But fog
Yes,
computing
sir.
is something different. Fog computing is it can move. Fog devices cannot move generally. It's basically the big servers of your college or your office or institution where you work, right?
Okay,
Yeah.
sir. Yes, sir. Yes. Thank you, sir.
And see, billions of edge devices are only millions, only few fog, only few cloud. So if you go to the down level, edge computing is much more powerful in terms of not the computing capability, in terms of richness, towards the IoT device. It is very close to IoT device, right? So that is the reason we are talking about edge device, edge computing.
Okay, sir. Okay. Thank you, sir.
IoT and edge is almost similar.
I think Shourav Mohapatra sir is having some query.
Yes.
And there is somebody else. We are not getting his name.
Yes, sir. Good evening, sir. I have one thing want to discuss with you. That is in this regarding. That is uh, in a slide you are showing that the drones are connected through the blockchain.
Yes.
My question is that as the drones are taking the data in real life scenarios, so as we know that the blockchains are forming their blocks in some slower manners. So how in real time scenarios the blockchain can be used
Yes.
so that the fast processing of the blocks can possible.
Yes. If you have seen
Is
my
there any techniques like
yes,
it?
yes. You see my IEEE transaction paper on consumer electronics.
Yes, yes, yes.
There we have published lightweight blockchain. It is already published. Lightweight blockchain.
Yes, sir. Yes, sir. Yes.
You
Okay,
search
okay,
it,
sir.
you get me with my name Devashish
Yes.
Dey, with
Ah,
lightweight blockchain. You have asked a very good question. The blockchain takes mining. It takes a lot of power and so and so. So we are now using lightweight blockchain. Okay, to
okay, sir.
provide this.
Definitely, I will go through this paper.
Yeah. Any problem you can contact me. I will show you. I can share you everything.
Oh,
Okay.
okay, sir. Okay.
So please share that. See that book of lightweight blockchain. It is published in last year, 24. Okay. Last year paper. If you do not get it,
Yes.
you can send me a mail, or I'll send you the paper, full paper.
Sure, sir. Sure, sir. Thank you, sir, for your kind help.
Yes, yes. You are from which place?
Sir, I am from TINT,
Oh, TIT.
IT department.
Okay, okay,
Sir, he is our
Oh,
HOD.
sir,
okay,
I know you
okay,
very
okay.
well.
Yes, yes. Okay, thank you.
Okay, sir.
Thank
Okay, sir. Okay, sir. Thank you, sir.
Yeah, lightweight blockchain is very much used for this kind of applications for edge computing, right?
So just for a little thing, I want to know from you that lightweight blockchain means in what sense we can make it
In
lightweight
terms of
means
algorithm, in terms of hash length and various other factors.
hash length. Okay, okay.
Hash length you can change also. Algorithmic complexity can change.
Yes, sir. Yes, sir. Thank you, sir.
Yes, thank you. Any question
Sir,
you can ask.
sir, before you proceed, just sorry to interrupt you. Our next speaker has joined. He's from
Yes.
California, Shubhashish Dashgupta, sir. At that place, it's 6 a.m. now. So it's sorry, sir, for waking you up so early. Sir has joined, and sir, there is one more question. I think another participant has raised his hand. So, dear participant, please quickly ask your question. Please unmute yourself.
Whatever we have
think
discussed, we have given in this book. Nilanjan is also part of TINT, so everyone know. We just published this year, few months before. 24.
Okay, I think he's not having any query. By mistake, he has raised his hand. So, Sir Shubhashis Dasgupta sir is there.
Okay.
And Shubhashis sir, Dr. Debashis Dey is now the presenter. We'll be starting your session just
Yeah,
few
I'm
minutes
just closing it.
back.
Closing it. Thank you. Thank you everyone for joining this event.
Sir,
On behalf- Yes.
dear participants, please will you quickly switch on your video so that we can have a photo session online in our edge computing devices.
Yes, you rightly mentioned. Edge computing everyone is using. Your laptop
Yes.
is edge, your mobile is edge, your tablet is edge.
Yes.
Can you hear me?
Yes, yes.
I
Yes,
just
sir,
want
you
to
are
make
audible.
sure. Okay, that's awesome. Yeah. Hello everybody.
So it's a like privilege for us to having two consecutive speakers in the same session. And it's combined session, and around 215 participants, more than 215 participants are there. So it's an honor for us. So dear participants, please quickly switch on your video so that we can have a virtual photo session.
Okay.
Thank you all. Uh, Devashi sir, do you have anything to share,
No,
or
no, already.
or participants any question you want to ask to Devashi sir?
I think they've already asked. And
Yes,
any
they have
question, I've
asked.
shared you my email ID also already.
Yes,
Definitely,
definitely.
I shared it with Madam also. You can share it to anyone. So those who are interested, you can send me email or WhatsApp. No problem. I'll give you the answer. Thank you.
I think we are not taking any break because as our second
Uh,
speaker has already joined, so we can continue, right? Saurabh sir and Kamala sir.
Yes, yes, yes. Thank
you,
you.
you could take 5 minutes break because I have to understand how to share my slides. Maybe a small break for 5 minutes would be great.
Okay. Then, okay, dear participants, then we are taking a small break of 5 minutes.
It's visible.
You can see it, right?
Yes, sir.
Yes.
Right.
There is someone in the audience who has raised his or her hand. Dear sir or madam, do you have any query to ask Debashish sir? Because sir has just completed his session. If it is so, please. We are again making. We have again make you a presenter. If you are having any query, please ask sir. You can now unmute yourself and you can ask any query if you are having.
Can you hear me again?
Yes, sir,
Now?
you're audible.
Okay, let me share and just confirm that you can see my slides. Can you see my slides?
Yes, sir.
Okay, thank you.
Sir, just let me make a formal introduction of yours. So, thank you, sir, for joining at this early morning. We are very sorry again to waking you up in this morning, and
That's
so
fine.
it's a formal introduction of yours. Dr. Shubhashish Rajgupta is a researcher at the San Diego Supercomputer Center, known for his innovative work in data management and security. He developed the awesome Polystore system, which has greatly improved the way complex and varied data are integrated and analyzed. His expertise has been key in important projects like National Data Platform and the Nourish project, showing his dedication to solving big special challenges through data science. With a strong background in access control and a range of important publications, patents, and books, Dr. Dashgupta has made significant contributions to secure data processing systems. His work connects scientific research with technological advancements, which are crucial for public health and national research efforts. Additionally, Dr. Dashgupta was one of the founders of the cloud management company Cavo Inc. Dr. Dashgupta has also worked on projects like DER Security and Quantum Data Hub, and was a key member of the China Data Lab, where he set up a facility for integrating information across China to understand Chinese policy, which was well appreciated by social scientists and legal scholars. He is currently involved in cutting edge projects like COVID-19 monitoring, hypertension, green energy, etc. He also advises various labs in medical and engineering schools in the USA, UK, and India. So thanks again, sir, joining. Basically, we don't have anything to thank you again to manage your time from your busy schedule. So over to you, sir. We are eager to listen from you.
Thank you, Dr. Bhattacharya, for your nice words and long introduction. It's all uh, I'm so as they say, as the introduction said that awesome is one of the work that I promote everywhere. But today's talk is not about the awesome. Today's talk is about something else. When we will come to the talk, we'll see. And Dr. Bhattacharya, do you think that we should start now?
Yes, sir, you can start.
Okay, okay. So, so I am Subhashish Dasgupta. I'm from my all education is from Calcutta. So I did my masters from Jadavpur and then worked at ISI for PhD. And there I work with the EC Electronics and Communication Sciences group. Then I moved to USA as a postdoc, and then from there I'm working here. So I belongs to this institute called University of California, San Diego, which is one of the part of the University of California system, where we have 11 campuses across the California. Some of them are like UC Los Angeles, UC Berkeley, and we have here in San Diego the UC San Diego, which we call University of California, San Diego. It was established in 1960. Initially, it was part of the UC Berkeley. Then they created as a full university. It's a location called La Jolla, which is at the Bank of Pacific, and the university is renowned for its work in biomedical sciences, oceanography, engineering. We have total 9 Nobel laureates home in this institute, and we do some kind of fundamental research on bioscience, engineering, and computation, smart health, electricity, etc. We have more than 35,000 students and 2,000 faculties. Each year we got a lot of Indian students here. So everywhere if you look at the campus, we have many great Indian doctors, many great Indian faculties, and lots of Indian students. In this institute, we have a department called University of School of Computing and Information Data Sciences, which is newly formed department, and now we belongs to that department. But before that, our institute or my department is called San Diego Supercomputer Center. It's actually a part of General Atomics Data Computation Center is started, and in 1985 it's formally joined SDSU as an organized research unit. So we have a non-faculty department. That means our department doesn't host any students. We have only PhD and postdocs, and we have several large computing systems, and we serve the researcher for their computation and data need. So basically, the researchers across the country, they join us to do their computation and research technique. So and that way we actually introduce with various different new scientific problem, and through that we try to solve with our computation, and we basically build the custom solution for different problem. San Diego Supercomputer Center is very known for their big data analytics, high performance computing, and in case national security, some advanced security stuff. Today we are going to talk about the wearable health devices. Now in this talk, when we talking about wearable health devices, that means the devices which user or a human being could wear, or in various form, like it could be a watch, it could be a ring, it could be a glucose monitor like Dexcom, or it could be a device which will basically tell you your hydration level, dehydrated or not. So these are the if you look at these things, so these kind of devices, they basically send the signal to the system and server, and then we analyze those system. And the great thing about the thing is it has app which could monitor your health, which could help you to understand the chronic disease management and other kind of stuff. Like, for example, if you look at this thing, this is a new thing. It's called sleeping mat. If you sleep on top of this mat, it will basically understand your sleep pattern, how much your deep sleep is, what is your REM, or what kind of do you have sleep apnea or any other kind of problem like that. And similarly, this is a heartbeat thing which will tell you a continuous PPG signal for to the devices. This is a Dexcom. It will measure your sugar level. So these are the whole lot of devices which is people are developing, and people are using those things these days at a scale. So application of the wearable devices are like better health management, real-time health monitoring, easy disease detection, etc. And in some cases, excuse me, it could be used for the chronic health management. And some cases it could be used in health management, like hemodialytic patient. Those have very critical condition, and you want to monitor them for various reasons, whether they have a fall or not, they have dehydration or not, they have cramp or not. So people are also developing those kind of devices for the very sick people, like a kidney damage or different heart condition. In some cases, also people are trying to develop devices which could help them or assist them for mental health support, or some kind of elderly people where you could support them with their real-time health monitoring, those kind of stuff. So these devices are very popular right now, and it has a great market thing. And if you look at the different kind of sensors which actually coming with these devices, you will see there are lots of sensors people are building for physiological sensor, for active motion sensor, environmental sensor. So different kind of sensor could measure this thing. For example, ECG, EMG, EEG are very common. If you have a 5,000 rupees watch, or maybe a $75 watch which could measure your temperature, ECG, heart rate, steps, because they have accelerometer, gyroscope to understand your movement. They have some kind of in some sensor they have UV sensor or humidity sensor which could help you to understand your environment and your health condition. So if you look at this, so I have listed all kind of sensors. So and their activity. So it's just like accelerometer could capture the physical activity, movement, sleep position, etc. We use people use some kind of ring for their sleep monitoring and sleep apnea, and they have monitored their sleep apnea, understand the critical condition of the heart, etc. And these days when I'm looking at the journal, I found that there are some new sensors coming along that could help you to monitor your blood pressure for 24 hours. Because earlier I remember, like maybe in the 5 years back, when people are coming with the blood pressure in the hospital, maybe everybody understand or who have blood pressure could have this kind of thing. Yeah, they know that which is called a white coat syndrome. That means when you will see a person with white coat measuring your blood pressure and your blood pressure suddenly got spiked. That means you're going to the hospital, you could see your blood pressure is increasing. Then it is impossible for the doctor to determine what is your blood pressure and how much medication you may require. On the other hand, if you have untreated blood pressure, it will create a basic organ damage, which is difficult. But if they put the more medicine on you, that also have adverse effect. Like those medicines have some kind of minimum or some kind of effect on your metabolism or your kidney, because those medicines are passing through your kidney or as an effect on your overall digestion. So one way of doing that thing, which is expensive, the doctors usually put you a blood pressure machine, which is stick with your hand for maybe 24 hours. We call that 24 hours ambulatory blood pressure machine, and that's like a real blood pressure machine, which it's you have to carry for whole day, and it's basically stick with your arm. And in every 30 minutes, that will capture your blood pressure while you are sleeping, while you are standing, and while you are doing some work or driving car. And in that way, we doctors or medical professional could get some kind of understanding of your blood pressure by after monitoring it for a 24-hour cycle. But most of the patient doesn't like that way very much, because it's, first of all, it's a huge device that you have to carry with you for 24 hours. But I have seen many patients, doctors are recommending go and get this 24 hours blood pressure. But recently I saw there is a sensor which could help you to get blood pressure in the 24 hours, and which is possibly change the treatment thing. Now this is a graph which is basically telling that total data, means these days total data that they're producing through these wearable devices in like a global measurement. So if you look at this thing, it has a spike from 2021, and it's basically exponentially growing up. So if you also remember this 2020 22 this period is one of the greatest period in our history where COVID pandemic hits the world. So when COVID pandemic hits the world, then we saw that this data production and analysis of this data and all those things certainly spiked up, because now people want to get more measurement through their sensor. They want to understand if there is any problem happening or not, any heart kind of issue or those kind of stuff. So we have seen a great development during this period, when more and more people are using this kind of devices. So you see, this side is the data produced in the petabytes. Now it's almost, earlier it was below 5,000 petabytes. Now it's producing 25,000 petabytes, and 2020 it was below 5,000, and by 2025 to 25,000 petabytes. So that more and more data every day. And also, if you look at the number, it will tell you the same story that 2020, and by 2024 or 5, it's total wearable app people are using. The 2010 or 2012, only we have a few running app, like most of the apps people are using, like running app from the Nike, or there was another app which basically capture your steps. That's all. But now it has different aspect, different kind of apps, which is basically bringing the data to the system, and they are producing a lot of data. So now also, if you look at the category, you will see that there is fitness app. Fitness app is still there, but health monitoring app, this green thing is growing. Also, there are sleep tracking app and the recovery app, which could measure how much you are fit for work and other things that are continuously improving. That means 10 years from now, this space will be a really hot place where you have lots of data, and you need to do lots of analytics on this space in order to understand the human health behavior, or in order to understand the chronic diseases. It will also help people to get more visibility for their health, and and it will help doctor to treat your illness. So here these apps are like, you see the 2020, the medical devices are also engaging with this kind of stuff. That also indicates that earlier most of the doctors or physicians, they believe that this kind of technology, or this technology is not producing much value in terms of treating illness. But now when they are engaging different medical devices, that means now they understand that looking at the data could basically change the whole scenario. So we started these things around 2020. Uh, in 2020, we got a project called TempPredict, which is a defense DoD funded project where we got a contract from a ring called Aura, and they have 60,000, initially they have 70,000 users, but then when they came up with the data and the quality of the data analysis, we got approximately 60,000 users, like, who are wearing that ring in various regions, and in California, and they have 1 year data. I will come to the data later, but they have 1 year data which we are continuously getting. And we got a contract from Department of Defense that we want to understand how this data behaves, and how we could detect early diseases, clinical illness from their thing. And during the same period, the pandemic happened, so we focused on temperature and pandemic relationship there. So there was the project named TempPredict. It's basically led by the University of California, San Francisco, UCSF Hospital, MIT Lincoln Lab, San Diego Supercomputer Center. We have the UCSD Bioengineering Department, and other many institutions. So if you go to the references, which is at the end of my slides, the first paper will tell you that almost 20 institutions collaborated on this project. So this is a huge, big project in terms of this kind of stuff. So what was TempPredict? Fundamentally, it was a research study focused on association between the dermal body temperature, that means basal temperature, heart rate related metrics, and onset symptoms like if you have fever, if you have COVID, if you have fatigueness, those kind of things. So these onset symptoms are collected through a survey, and the dermal body temperature and the heart rate are basically collected through the devices. And it's during 2020 early we designed it for the COVID-19 symptoms. So basically, in ground reality, we are contacting UCSF hospital for this survey, and we are collecting this data of the temperature, heart rate, and other related data through the through the ring. And how the technology will come back today. So we have some slides there. So purpose of study there, collect data from sensor, develop an algorithm which could predict the symptom onset here. Symptom is COVID. So can you predict that the main fundamental question is, can you predict this person requires a COVID test or not? And this project was during the COVID pandemic. We were running this project in live. That means every day we got this data from through the API from the Aura, and then we run our algorithm on the data, the machine learning algorithm. After cleaning and processing the data, we run the machine learning algorithm, and we try to predict that this person may have a possibility of COVID or not. If they have the possibility of the COVID, then we call the hospital to ask that person to come to the hospital for COVID test. And that was pretty good. We created an initial data set and then create the model, and model was just looking at the cohort that's basically predicting the COVID. So, but the goal was basically to early illness detection, which we extended for beyond the COVID towards different diseases. We created a pregnancy, women's health related thing, and other things. But that time, initial study was indicating the visual change in physiological measurement like body temperature, heart rate variability, respiratory rate, how much oxygen that person is getting intake, and we are trying to do the early illness detection. We develop a basic machine learning algorithm. Why I'm telling basic, because we could that time basic machine learning algorithm we used because we want to do it faster, because we have a 24 hours window and we need to run everything on top of 60,000 users. So that's a huge goal, and we need to, within this 24 hours window, we need to clean the data. We need to predict the data by running those model. We need to call this UCSF hospital about the symptoms, and then they will call the patient to come for a COVID test. And the whole drill, like it's a 24 hours things, because we are doing it every day. So we created a validation of a multimodal model, because we have different kind of physiological data from different sensors, because one ring contains multiple sensors, and we have survey data. So basically we want to create a multimodal model data which could improve the accuracy. So, and it's also have the public health implication, because during the pandemic hits like very bad here in Los Angeles and San Francisco, in New York. So enter United States was like looking for a way to understand how they could improve the public health. So in that way, we were doing this study. It was very important because that has a bigger effect on the public health, so that our hospital could detect this kind of diseases early, and they could they could do something like giving some kind of medication, although that time vaccine was not there. So kind of medication for those kind of stuff. So basically they could isolate the people, they could test their COVID early. So we are just trying to stop the spreading of pandemic in a real life, like it's like firefighting. So the main challenges we saw in this data was the sensor data, which is true for later. I understand that which is true for any kind of wearable sensor data is the limited accuracy, because these sensors are if you look at the communication perspective, these sensors are not great about the accuracy of the data, because when you have duplication of the data, sometimes you have missing data point, sometimes people doesn't sync the device with the cloud, so you have like a missing period, but later when they sync the data, that could fill the missing period. So you have basically bitemporal nature of the data. One temporal, but that means they have two kind of time thing. One is when they're syncing the devices, and when you are looking at the data also itself has a time, that from this time to this time this person has a respiratory rate like this time respiratory rate like this, temperature is that. And also in some time people doesn't wear the devices. So if you don't wear the devices, but devices is not at least that time devices were not that smart enough that it could detect whether somebody is wearing or not. It's still generating the temperature data there. So that means a whole lot of data where data is there, but accuracy of the data, validity of the data were very questionable. Then we have also in the physiological data, they have the population is very diverse. They have different age, different sex, different pre-existing condition. So modeling those data is kind of a heterogeneity in terms of the cohort selection. So so you just cannot go and just select a population and try to build the model. Will not work, because in that model you will have different different demographic, different comorbidity, etc. So heterogeneity of the data was one of the issue there. Then we have sensor was not from the same version, so we have to scale as well, because data was if you look at the watch, you will see they have which actually capturing the data, and everybody maybe in the second or microsecond. But when you are creating those data, you need to scale those data, and we decided to scale it for the 5 minutes, because doctors told that scaling in a 5 minutes for any biological variable is fine enough, because within 5 minutes what is happening, you could do the average of that, and that's fine from the medical perspective. But we have different problem on scaling about data, that suppose for one person for the 5 minutes you have 3 data points, but another person, you within that 5 minutes they have 10 data points. Now, when you are doing the statistics, you need to know this average is coming from this many data point. This average is coming from this many samples. So we have all those kind of challenges to clean the data. And then I already mentioned there is a diverse population representing the data from age like 20 to 60 to 80 and different condition, different medication, pacemaker and other kind of stuffs also involved. So overall, finding the training and other stuff was complicated, and looking at the data, cleaning, creating a proper cleaning mechanism was also complicated. So those are the challenges for data cleaning, and also we have different challenges for modeling because of the heterogeneity. So in the temporary study, we use Aura ring. It's and the first page we have the picture of that ring. So this is basically the Aura ring, and you see here inside the Aura ring you have multiple sensors, and they will recommend. If you ask them to get a Aura ring, they will measure your finger, and then they will send you this ring to you, and this green, red, and other things are the different sensors. So if all those sensors are collecting those data like heart rate variability from the PPG data, they are basically deriving this thing with their algorithm. And then we have a temperature sensor, and we have a respiratory rate, activity level, etc. And in the survey, we are sending and calling the patient to fill up the survey form, which contains different kind of comorbidity, whether they have fever, fatigue, cough or not, whether they are doing the COVID test or not, those kind of their age, their other symptoms, all those things in the self-reported data. But how much you will rely on the self-reported data, that's a questionable thing. But we use that self-reported data to understand the accuracy. The scale of the data was after all those cleaning and those things. We have ballpark 60,000 patients globally, and we created a longitudinal data collected from daily for weeks or months. So basically we have a big data set. And purpose of the data was to train a machine learning to see the early sign and identity of the individual's baseline. And then we have second challenge was anonymizing those data to store at our HIPAA server. But that's not that was a different challenge, but we are not discussing that today. So looking at the first, let's discuss the temp predict architecture, how we created the overall architecture to create that thing, because that's one of the topic, that how we will do these things in the cloud. So we created a whole thing in a large but private cloud. So I will also share the architecture here. So architecture basically designed to leverage the wearable devices data such as temperature, heart, and other things. The pipeline was like this. We have a data collection, then we normalize the data. Then we created the feature extraction and the engineering. Here we have among these 60,000 patients, we have a model of 2,800 data. Those are manually labeled for the training purpose. So basically, we have 2,800 data. We know they have COVID, and they have their whole heart rate, temperature was there, and we have survey of them, and we created the model using that data. So machine learning model, this model training was done on 2,800 data. Then using that 2,800 data, we created a prediction model of that. So this is the templatic architecture component which we use here. So basically, these users are analysts. we have a temp predict team interface, which is basically a Jupyter hub, and through the Jupyter hub, we have different clusters running here. Through the Jupyter hub, you could basically connect to this timescale DB. So timescale DB is a database which handles time related thing. If you go to a normal database, by its nature, suppose you go to the Postgres, by its nature they don't have time related algebra. So if you want to do a time related query processing, which is heavy, so you need to go for a time series database. Timescale DB is one of the time series database which is built on top of the relational database Postgres, and it very basically has some extra ability to create time series related index, and it could execute the time series related query on this database. So if you look at the awesome S3, we are basically collecting the data from the Aura, and we are storing here in the Amazon S3, because that was the Aura's part. Every day they collect data from these rings, and they store it on their cloud, and from their cloud we are transferring this data to Amazon S3, and we have a Sherlock secure cloud services at the database, which has all those security primitives and all those security notion installed here, which is basically make it very secure. And HIPAA means the health standard compliances through their process. So basically, what we are doing, we are pulling the data from devices. It could be a API, it could be a devices, and we are storing the data on a daily basis to the timescale DB at inside the Sherlock. If it's in a small scale, we could directly pull that data from the Aura's cloud API services. Means most of the devices, if you look at this Fitbit or Apple Watch or Aura, they have a API which is they call the self shared data. You could basically call that API to get the data and store it into a secure location. But here our data set was 60,000, so we use Apache Spark to transfer data from Aura to here, which was under our internal contracts through the Department of Defense. So basically, we don't need to call the API. But the alternative, we could call the API and get the data, which was time consuming. After storing this data, we anonymize the data and move it to a relatively non-HIPAA compliances here in the awesome storage. The reason we are transferring data here because it's more computation friendly and it's connected with our big blocks. It's called Nautilus. Nautilus was a community driven distributed large computing facility which has thousands of GPUs and CPUs and memory. This is a Kubernetes cluster which is running across the America, and we are basically could access that data from here. But we cannot we cannot connect Nautilus to the Times Sherlock because of the security. So we basically move the data here to get more computation, and then every day we try to run the cleaning pipeline and then scale the data and store the data in the timescale database. After storing the timescale database, we use our machine learning module to run on this data and predict that thing. And we use predict the subject. And when you have the subject, then that basically sent to the UCSF hospital to call them. So this drill, this whole architecture was processing once in a day, starting from 3 a.m. in the morning, and it's done by 7 in the morning or 8 in the morning, so that we could send information to the hospital. There are some architectural details here, like we have persistent volume here in the Kubernetes cluster. We have some cloud repository, and we have lots of hardware related to this place here. So once we got the data collection, and through the ORA integration, we will getting all those data in our locally at the Nautilus cloud, and we have I already explained this thing that we have a data transmission to the cloud, which is which is encrypted and ensure for the security and the HIPAA thing. And so the API, the cloud infrastructure is actually integrated with the API. And if you go to the API, so basically, you all possibly know better than me how to call an API. Basically, when you are calling the data or requesting the data, API asks you for the author access token, and they have a mechanism that in all API, like if you go to this Fitbit API, through the now it's Google, so through the Google, so they will ask you to create a app, which app basically connect with your health data, and you need to create a bearer or access token for the API, and that token expires within 4 hours. That means every time you are collecting the data, you need to first refresh the token, get a new token, and then you have to collect the data. So we did that thing for Fitbit in a different project, but that is like a quite standard thing to do. You have authorization bearer token in every API call, and then when you will request the API, it will send you the data, and you could store the data there. Like for this example, like we have a device ID this, and this is the temperature, heart rate, HRV, etc. But if you want to get the direct PPG data, possibly you need to contact them. Most of the time, what you are looking at this rate, they basically get the signal from the sensor. Then on that signal, they run their algorithm and then predict your heart rate. So there is a possibility of error here, but that's fine because it's how the error is not that much. So people work with this number from the API. Very few people very few people analyze those signal directly to do that, and it's hard to get the signal also. So once you have, so you could means if you are doing similar kind of thing, possibly it's better to get through the API. Otherwise, some cloud provider or some service provider, they could give you the same set of data with some charges, but those are expensive these days. Maybe there is a company called Fitabase. Fitabase, they sell the Fitbit data. So if you ask for the data, they have all those things set up, and they have internal contract with Fitbit, so they will have better privilege to collect your data, and the granularity of the data will be more granular. So but they will charge you subscription to collect and deliver those data. So that's the second way of accessing the data of these wearable health devices. So first way is if they have API, most of them has API. You could go to the API and collect this data by yourself. Otherwise, you could ask a company to collect your data, and they will charge. The charge is huge, by the way. So in the temp-predict data, let's coming to the temp-predict data details. We have 60,000 patients, and we have 5 to 10 features we are calculating, and time series data was daily observation over multiple weeks, and total we have like a 12 months more. Total data set is like a 56 week or something like that. The temperature data is continuously monitoring, and for example, we are continuously monitoring and normalize the time series of the temperature data. We are before normalizing, we are also doing a correlation check. Like we are looking at the accelerometer. If the accelerometer is in the in temp predict language, they call is MET data, metabolism data. That's actually coming from accelerometer. And if you move, even in the sleep, you are moving a little bit, it could give you a higher signal than the threshold. That means looking at the same time point when you have little move, or your accelerometric data is little high, then we could tell that that time that person was wearing the ring. And if the person was wearing the ring, we could say that that point of the data for temperature, heart rate is or respiratory rate is a valid data, because it's not the case that they just charging the ring or putting the ring in a bedside table and sleeping. So when the person is wearing the ring, it's very critical for our analysis. So we are basically using that data to clean up our process. Then we have the missing data problem. So we use data imputation technique, like number of n was possibly 21 or 49 something. I have that number in the slide. So we basically imputed the data and scaled the data to handle the missing data. We also use the standard z score or z score to do the normalization. So and leveling the level the data, we have, as I mentioned, we have a set of level data for the COVID related thing. We did the symptom onset check, then we did the diagnosis and physical thing, and then we have an input feature of the training data, which contains all those temperature, heart rate, variability, and other things, and and our success was measured by the AUC, that's area under the curve, which is 0.8, which is, we couldn't say that's a great success, but that time it was quite notable, because no other technology was there to do this stuff. So I described how we are handling the data. It's very plain and simple. We impute we did the missing values. We handle the missing values of the time series data. We did some imputation, and we also did some outlier thing, like who has, because in this prediction model, if you put the outlier data from the ring, either it could be for the technical problem of the ring, it's sending wrong data or something else. So that could basically ruin the whole effort of the model. So we basically remove the values from by doing median absolute deviation from the baseline. Then we did the normalization. Whoever practicing machine learning could do better than this, but what I want to say that we did the mean and standard deviation for over 21 days, and if they have missing data, we possibly moved up to the 49 days. Then we did the temporal aggregation of the data for the data granularity and the time scaling. So basically we got a valid data for our known time period, and then we aggregate them for the temporal aggregation. And for this temporal aggregation, means we use timescale DB SQL query to do those kind of aggregation. So this normalization and these things, We have not written any line of code. We use SQL to do that thing because during that period with the rush, we don't have time to write the code. So we thought that SQL could be a good thing which we could use in which we could use in an efficient way to solve our problem. So we use that. So we reassemble using SQL in the time scaling. We did this thing. These are we rescale the data in 1 minute and 5 minutes. If you go to the time scale DB, you will see they have a thing called time bucket. If you run those time buckets with different granularity, they will do the time scale thing. And also we rescale the accelerometric data in the 1 minute level, so we could understand that person is wearing the ring or not. In that way, we improved our efficiency of the model in a better way. Also, as I mentioned that validation, we did a kind of validation. So this is the rescaling thing. You understand that from the 1 minute we did this integration. Validation using accelerometric data. We validate the data from the accelerometer. As we mentioned, that accelerometer was one of the key indication that whether that data is real or not, or that data is valid or not, because that only indicates that whether that guy is wearing or not. So we basically use the accelerometer to do these things and correlate the different level report behavior of the data. So there was a whole pipeline we did, and I already mentioned the normalization process, and we created a 21 days baseline. If the 21 days for particular subject, if a 21 days baseline is not enough, then we move to the 49 days period. So we put a purpose to do this baseline design, because if you remember, I mentioned that our data was very heterogeneous, like they have different cohort, different age, different kind of people. So we apart from handling the missing data, incorporate the temporal pattern. The purpose of the baseline is to also handle those demographic variability. For example, so we basically try, the baseline design. The main objective is to ensure the robust normalization for individual, because individual we will come to that thing where I want to establish my points here. So we ensure the normalization and enhance the algorithm here. We use the diverse cohorts. That means the condition, gender, etc., and provide a foundation for detecting significant health derivation, such as whether that person has a pregnancy complication, because whether they have a preeclampsia. Those conditions we bring to the cohort, because otherwise that could affect the model. And also we want to remove all possible physiological bias of that person looking at the data. So we designed the baseline, but you really understand that there's no single baseline here. We actually have designed a few baselines here for different cohorts. So here we as I mentioned that we have different baseline cohorts that which is the minimum of the N1, N2, and N1, N2 is the different baseline size. So we basically design the minimum of these all cohorts in a common baseline to create our model. So this is a example of if the baseline is reliable baseline design. So you see there is we computed the z here or z here, where we have the x and we have the mu b 36, and so we computed 2.33. So that's the reliability measurement. And we have, if we have insufficient data, is not 21 days, we created the 49 days things. And this is an example of demographic adjustment which we did. So we also did a circadian adjustment, looking at the circadian rhythm of the person, the sine curve which is there producing because of the body clock. We also did a circadian adjustment with the model. We also work for the high dimensional feature space and overfitting. So doing those things, we got these things. We got, that's the success part of the thing. But there is a failure part, I will tell you, where we after doing this thing, because you remember that why I am explaining all those baseline design, because I want to say that we did a very detailed work to capture all those cohort, comorbidity, and other kind of conditions from the population to construct a predictive model which we could use. And we got some kind of success which we showcased in our paper published in Nature in 2021, where we say that we diagnosed 2.75 days before the testing. That means uh, mm, when you have some symptom or visible symptom, where you could say that this person could go to the for a COVID test, we could actually predict that thing before 3 days. That means before 3 days, actually you are getting a period to isolate that person and go for a COVID test. We have a quite good, like a accuracy of 0.819, and we demonstrated the value of temperature monitoring with a 4.9%. We highlighted the diverse population, and we have scalability, and this is the result we got. You see, these are the false positive rate of this population, and the population is defined. It's possibly it's better to go to the paper to see that. I have that paper public and in the reference, so I'll give that reference later. So, but we got this kind of success here, but we have we having those success. We also analyze the data, and we found that for a particular population, we haven't done a good job for the women. So all the patients, we told that you could have a COVID, and you go to the testing, and testing came out that it's negative. That person doesn't got any COVID. Those populations are mostly the women's between age of 20 to 50 or 55. So that's a phenomenal and like a very surprising discovery, that why our algorithm was so biased on that perspective. So we understand that later that this during the ovulation time or during the menstrual cycle, the women have a temperature little bit elevated. System is capturing that thing, and as in our algorithm, we said that thing as a primary influencer or a major influencer. So that was actually giving us a wrong signal, and we sent, and that was a major part of the error. So even with this success, we realized that this analysis is not perfect. So then we have later our lab in the bioengineering department, they started doing more research on this thing. But after temporary, we did a few things. We moved to this direction, that continuous physiological monitoring, and connect that with the psychological health and other stuff. So we are basically started doing another project called StepNet, which is funded by UCSD for the hemodialysis patient to measure their steps and how much they are working, because the hemodialysis patients has basically they have 3 times in a week dialysis session, and their both kidneys are not working. So in that case, if you put more medicine on that, their metabolism is not improving, or it's an adverse effect on them. So we want to demotivate through our intervention method, through the text intervention or any other intervention, maybe a video intervention, and ask them to work more to improve their physiological thing. Then we try to improve our feature engineering, because clearly we have some problem with our feature engineering in our paper which we published earlier. So we created feature engineering from different perspective. Also, we add the mental health is one of the feature engineering thing, and the debiasing technique, because debiasing technique we need to create a debias algorithm which could actually adjust the model for women's of that age, or some pregnancy thing. We have a, we later we this year we published another paper at Nature Journal of Women's Health for this technique. So we understand the fundamental problem with human physiological data modeling here. That means we understand that when we are doing other kind of modeling, like modeling of any other physics driven thing, or not even physics driven thing, some kind of other modeling, that is quite different from modeling a human, because of this, that baseline, every people, we observe that every, and they are, depending on their age, their, example I said that woman exhibits higher body temperature. It's basically those influencing factors should be taken into consideration to technique that from person 1 to person 2, depending on their sex, basically could have a few influences or adjust their thing with pressing to that's just an example. Machine learning on one side should not fit for all in generalized machine learning model for all. How we could incorporate the individual differing for other technology or other, you have to do something else which maybe more targeted to then also you have to incorporate the demographic thing with the other factors. So that means if data processing should be different, and data processing should be different, then your data debiasing normalization technique should be very it's very tricky, because you have to understand the cohort, you have to understand demographic, you have to understand that human nature, and then you have to bring that thing in the system. And in modern days, if you go to any car shop, like a good company's car shop who has those machine learning system, they will plug in your car, and they have created a huge cloud which will analyze and tell you the which portion of the car should break up in future, or where is the problem. But advantage of that car is, if suppose it's a Volkswagen or Toyota, or something more like a BMW, all their cars behaving almost like same. But here human doesn't do that thing. Human has so many variability, starting from demographic to their health practice to their age. So you cannot apply a, a basic car model or a Tesla model to a human because of its complexity. So biological models are one of the most complex model. Their lifestyle is so like the people differ because of their baseline heart temperature, their influencing factor like how their heart rate is, how their sleep pattern is, what you call sleep apnea or other things, and then you have to incorporate the adjustment with that. And we discussed the adjustment, the possible adjustment technique, but those are not enough. Then another thing is the second general idea I understand, that normality in the biological science is difficult to define. In a data, we have the one of the why normality is challenging, because biological system exhibit inherent variability influenced by the circadian rhythm, body temperature, your environment, where you are exposed to a pollution or not, where you are living in a high altitude or not, everything. So you don't have the normal distribution from population data. Rather, you have different kind of normality. For example, look at this picture. This is actually Patrick published in a conference. So you look at this data. So if you look at these green lines, they are basically telling the heart rate average. And these green lines are different average. They are basically moving from the population normal. But is that wrong? Like having, suppose population normal is 60, but your heart rate average is 70. Is that a wrong thing? It's not a wrong thing. That's your heart average. But the interesting thing is model cannot impose this is as a normal on your heart rate model. So suppose you are a very good athlete. You run like a 10 miles every day. So in rest, your resting heart should be here somewhere, like 50. So I cannot just use a generalized model to understand your heart variability for the analytical purpose. Similarly, if you look at this thing, you could easily understand that although we have different age, but it's hard to find the normal thing. Also, it's for the algorithm design, it's same. So suppose we map those things in 2 dimensions for the population, you will see different normal in a different position. And if you want to design a specific you want to design a model to understand specific target, you will basically have many targets. So for many class of people, it could be not 4, it could be many more. Many class of people, when you are designing the algorithm, your normal would be definitely different because of the particular age, comorbidity, and other kind of biasness. So your algorithm should be different. So so one thing is my so how we will define this normality. So right, so this is I don't know much about this thing, but this is one of my idea that we could if we want to handle this kind of data, we should for analytical perspective, we should definitely go to the time series anomaly detection or time series analysis in a broader scale. So there are few groups, they are working with these things. How to analyze the time series data for anomaly detection could be one way to understand this data better. So what is the anomaly detection? I'll just give the definition, and I'm not an expert of this thing. I'm still studying how to do these things. There are few papers in 2024 and 2023. So I'm still trying to study in this space because this application could be extended for healthcare, for IoT, for finance, for disaster management. The key concept is we may have a point anomaly, which we are basically trying to debias thing. We are trying to come up with the missing data, but the most important is contextual anomaly, which is different from different contexts. Like a person with a comorbidity with blood pressure is maybe different with a person with a comorbidity of sleep apnea and high diabetes. So it could be different. So we want to cluster those data in an anomaly cluster series to predict the value of the xt. So basically, if you go to Iman Kiyov or any other group's paper, they are trying to understand this behavior from the time series data, which we could use here for clustering purpose. And we could use the LSTM transformer model to do this thing, but I don't know how much deep learning could help here, but hopefully with a new algorithm, deep learning we could use a transformer model to do this thing. So here so now the question is, in a deep model, they have a big success is the large language model. Large language model changed the whole dimension. Now the question is, how we could use the transformer model to understand all these things, because when I'm looking at the large language model, I could see that it could easily identify many things. Now whether it could identify this kind of data, this kind of biological data with their extension, that's an open question. Interpretability is a problem, but yeah. So now the last part, which will conclude the thing in 10 minutes or less. So how we use the HPC? So basically we use HPC because of its benefit of scalability, real-time anomaly detection, and you could basically scale up all those things, enhance the health monitor. So the cloud analytics is basically using this HP cloud architecture. Doing all these things is very easy and flexible, so we could use that. I use Kubernetes over the conventional HPC because one of the thing is Kubernetes is flexible and it's transferable, because you are doing something, or we have large Kubernetes clusters here, so we could use those scalability, and we could move one cluster to another cluster. We could do a dimension change. We could scale up the thing very quickly, and it's distributed. I don't need to bother about many of the things. It's done automatically. So I use Kubernetes, and the role of the Kubernetes is the edge node is basically cluster in a cluster, and you could basically allocate on that cluster. So it will contribute in a distributed manner, and it's create a small cluster for you where you are working. So that's Kubernetes management. And if you and there are many providers these days. We have a platform called Nautilus that is actually came from this Pacific research project of Optibuter. That's Optibuters means it's optically connected computers, like a laser connected computers, and it's a Pacific resource because it has a portion in Japan and a major portion in California. So we have optibuters across the Pacific, and we could use both the country could use these resources very efficiently. And we use the federation of the Kubernetes cluster from the NRP, and we have the federation, which is actually, if you go to the National Research Platform US, you will see this federation thing. It has many clusters from New York, from Omaha, from MIT, and they clustered this thing for the federation. Using this Kubernetes, we could basically allocate on this cluster. Uh, we could use the Kubernetes role, and it has some kind of privacy because I mentioned that we have a could use our private computation, like when we are collecting our data from the Aura, there's a risk of it could expose the identity, so we use the privacy preserving thing. And we could combine the weight from now we are trying to combine the weight from the Sherlock and bringing the weight out. So we are not actually moving the data, we are basically moving the weight, which is a fundamental thing of data stays at the site, and the computation model goes to the data, create the weights, and then bring the weights out from that site and combine the weights in some common location, and then they perform then they do the other kind of use of that model. In that way, you are not really moving the data, you are just moving the weight. So that's kind of arguably that's a privacy preserving technique. So we do the load balancing and other things. So here are the goals why we are using UCSD, Nautilus, and NRP. But unfortunately, Nautilus and NRP is not open for outside, but we have alternative. So this is the way how a Kubernetes script looks like. You can basically create the resource limit. You could put your resources here. You could bring your own images, and you'll run. So in that way, if you have a Docker image which is fully configured, you could basically use with your hardware to do that thing. So it's easy. It's just like a simple YML script, and run it, and it works fantastic in a fantastic way. Similarly, you could do the load balancing, auto scaling, etc. with the scripts. So it's flexible. It's flexible. So I usually promote the Kubernetes for computation. It has some downside, that's fine, but for our computation, for our flexibility, it's awesome. But so yeah, as you don't have the access to this, it's called National Research Platform in United States. If you have access, that's fine. But if any institute could add you if you have connection with them. You could go to the provider, like they all have Kubernetes thing. Amazon, Microsoft, IBM, Red Hat, OpenShift, DigitalOcean, and these dollar basically represent their relative cost, which is from my point of view. But all they have a free tier. So basically, what you could do, you could write your Kubernetes script, or you could ask your students to write Kubernetes script and run in this cluster free tier. And then, if you have some funding, you could move to the paid tier for do better computation and use better GPUs there. So we will also have some other thing, like Oracle. They have Kubernetes. I know there is the Alibaba. This is one of the hottest thing. That's Chinese company. They also created they have created a very good LLM model, and now they are providing a cloud container service. So it's only to check Alibaba if they have good deal. So the main main thing I want to conclude here that although we have so this kind of computation, like you understand this human thing with the wearable devices, you need to go through very minute details for the cohort. You need to understand the exactly human behavior, and then you could model the whole thing. Otherwise, it will create a false result. Second thing, there's something called digital twin, but we are not yet like a 1% towards that for creating a human digital twin. It would be very interesting, and in next 10 years I'm pretty sure that that would be one research direction where capturing all those medical devices, capturing all those labs and the wearable devices, you could basically model, you could basically see people are coming up with the digital twin of human, which would help medical system in a tremendous way. Like you have your heart having trouble, like if you have a stroke, before the stroke, at least 3 months before the stroke, there was a symptom that could tell you that your blood are getting clotted. They started early, and if you could, if any of the device could capture that thing, it could save you from a stroke. It could save you from a heart attack. It could save you from any sudden thing like internal hemorrhage, or even for a viral attack or something like that. So those days are actually important, and important, and those things are important, and those days are coming, and it is also important to see how it's going. I presented a very preliminary result here, which is like possibly near about the zeroth level of this research, but this is one thing which possibly could impact the future of computation and resources, and research toward the digital health. We published a few papers. This paper is the technical. We have the IEEE big data paper. This is also the little bit vaccine medicalist paper. This paper the published in scientific report Nature, and this is basically this is fairly popular, and this will tell you the study of our TempPredict, the first study. Then we have, after that thing, the human health, and I think we have a couple of PhD students. I'm also co-author on all of these papers. So Patrick, he created a data analysis here. It's in the sensor, and Lawrence actually working on the women's health. She just got her PhD, so that is a recent work. And also Lawrence published another recent work here. It's more because the other guy, the Jamie, is working with here, so it is more around the computation and other things. So this guy will actually going to the time series analysis direction. So that's all about my talk. This is my details. You could feel free to send me an email here. I'm slow, but I will answer. I will definitely answer those. That's all, Dr. Bhattacharya. If you are around,
Yes, sir.
1 minute.
Yes, sir. Yes, sir. Now I'd like to take questions from the participants, if there is any. But before that, sir, we deeply appreciate your time, effort you invested in making this session. Like it's so informative. Thank you again. Now, participants, if you are having any query or any questions that is there.
And also this is my first effort to present this thing in any public forum. So I never presented this thing before
Okay.
anywhere. So I know
And
there are
sir,
many
there is
mistakes, and
more than 200 participants are still there. So I think participants, if you're having any question, please feel free to ask, sir. Even Devashi sir is also there with us. It's we are
oh
fortunate.
my God.
Yes, sir was listening to you in the entire
Yeah.
presentation.
Thank you for listening me, but I don't know whether I did a good job or not.
Okay, so sir, it will be kind enough if you share your presentation with us because participants they will have to. Sometimes they ask for the presentation, so please do share as per your convenient time.
I will share the PDF with you.
Okay. Yes, sir. Thank you. Kamala sir, do you have anything to share or?
No, earlier, probably Professor Farooq had some query. He raised the hand, but probably he is not in the meeting right now.
I will answer if somebody send me an email. I will try to answer those things.
Sure,
Sure,
sir.
sir.
Okay, sir. Thank you very much. Participants, please quickly turn on your video so that we can take a snapshot of this session. Yes, it's a matter of 2-3 minutes. Participants are requested to turn on their videos.